Recording in progress.
Okay, good evening all. Everyone can hear me? Online students, is my voice is loud and clear? Okay. Okay, guys. So let's start the session. In the last class, we have discussed about the simple linear regression and we identified the relation between the total spend versus sales. In today's class, we are going to work on the multiple linear regression. Now, what is meant by multiple linear regression means, again, we are linear regression, same linear regression. We are assuming the relation between input versus output to be linear. We are assuming the relation between input versus output is linear, but this time the input variables are multiple input variables. The relation between multiple input versus output variable is linear, which is a multilinear regression. Okay. Now here, as previously we explored, there is a relation between total advertising spend versus sales, as well as predicting the total sales for the sum value of the total spend. We have predicted the value. Now, in this case, what we are going to do is, what is the relation between each advertising channel, that is TV, radio, newspaper, and sales. So this is one of the most important multiple linear regression. In the real life, we'll apply multiple linear regression only. In the few cases only, we are going to have the simple linear regression, but every time we are applying the multiple linear regression. Now here, first I'm going to import NumPy, Pandas, Matplotlib, and Seaborn. And along with that, I'm going to load the data set called as advertising data set. Okay, same. Yesterday, whatever we have done, the same data set once again. So again, if you observe this TV, the TV and whatever we are having, TV or radio or newspaper, everything are continuous. This is a continuous variable, radio is a continuous variable, newspaper is a continuous variable, and sales is a continuous variable. And output is a continuous. So we are going to apply the regression. So first we are going to apply the info. In the info, we are going to get 200 records with the 4 columns, and we are going to check, is there any missing values? Miss, there is no missing values, right? Now we are going to do the data pre-processing. In the data pre-processing, first we are going to do the describe function, that is basic descriptive statistics. And second one we are going to apply is pair plot. And we are going to see the pair plot and the relation between input variables versus output variable, how the relation. So from this pair plot, we can observe this is the output variable, sales versus TV. Sales versus TV. This is the scatter plot between the sales versus TV. This is the scatter plot between sales versus radio. This is the scatter plot between sales versus radio. This is the scatter plot between sales versus newspaper. So these are the 3 scatter plots which I want to see. So just if you observe, here I can fit a linear line. Here also I can fit a linear line, but the distance between the data points is very high. Here if you observe this one, the distance between the data points is low. Along with that, I can't even fit a linear line, but still I'm assuming it is a linear regression. Okay. So here, if you observe the distance between the points, whatever the data points, the distance between the data points is there. The distance between the data points is somewhat close, but in this case, the distance between the data points are somewhat far away. And here it is too far away. Now, what that is indicates in the scatter plot, if the distance between the data points is very close to each other, what is the meaning? If the distance between the data points are very far away to each other, means what is the meaning? Means if distance between the data points are very close to each other, very tightly packed, means the correlation will be very high. If the distance between the points is far away to each other, means the correlation will be very low. Okay. And here, if I observe this correlation matrix, so I'm going to open the correlation matrix, and you can see here the correlation between TV versus TV is 1. Obviously, with the same variable, it will be 1. Radio versus radio is 1. Newspaper versus newspaper is 1. Says versus says is 1. So the diagonal values is going to 1 always. And TV versus radio. What is the relation between TV versus radio? The correlation between them. The correlation between TV versus newspaper, TV versus says. So here the requirement is between the input variable. This is the input variable. This is the input variable. This is the input variable. And this is the output variable. Again, input, if you write like this also, input, 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 and output. Now I want the relation between input versus output. Means this one. This is called as input versus output. Here, this is the relation between input versus input, TV versus CV. This is the relation between input versus input, that is TV versus radio. This is between the newspaper versus TV, TV versus newspaper. This is the value. I don't want between input variables. I want the relation between input versus output. That is nothing but TV versus says, this one, or says versus TV. Anything, both are same. This one and this one, both are same. This is the first one which I'm going to observe. What is the relation between input versus output? 0.78. That too, it is a positive value. Positive value means the relation is positive. As x increases, y increases. And from the scatter plot also, we have observed the same. As x increasing, y increases. Next, if you observe here, this one, next one is 0.57. The relation between input and output is 0.57. The relation is comparatively, it is low. Can you see that relation, correlation? Because the scatter points are also far away to each other when compared to this. What are the data points are there? Here they are comparatively somewhat close, but here they are comparatively very far away to each other. Next, and we are having the correlation of 0.22. 0.22 between input versus output. That is TV says versus newspaper. The relation is 0.22. This one and this one both are same. Whether you are asking newspaper versus says, newspaper versus says, or says versus newspaper, both are same. Two variables are same only, na? Whether it is a newspaper versus says or says versus newspaper, the concept remains same. Why? Because the reason behind that is formula. Whatever the formula we are having, x into x bar into y minus y bar if you apply, or y minus y bar into x minus x bar if you apply, also the answer is same. A into B, B into A. Both are same. If you multiply this one into that one into this one also, answer will be the same. There will be no difference. Okay, this one and this one both are same, right? So that is the reason we are having in terms of the upper triangle and lower triangle matrix will be the same. Right. Now here, there is a most important point. The relation between input versus output should be very high. Should be high. The higher the correlation value, just focus, later you can write, I'll give the time. The higher the correlation value, the better the model. The higher the correlation value, the higher the R square you get. The higher the R square we are going to, okay, the better the model. Simply to say, the best model we are going to get, better model. The higher, the better the model we are going to have. The relation between input and output variables should be very high. Okay. So if the relation between them is high, means we'll get the better model. If the relation between them is 1, the correlation quotient is 1, perfectly it is 1, that is the maximum value. Whether it is a +1 or -1, the absolute correlation quotient, the absolute value, whether it is in the negative direction or whether it is in the positive direction, the absolute correlation value between the input and output variable should be maximum. The higher the value, the better the model you are going to get. The higher the R square should be the maximum. We have to get the maximum. The relation between input and output should be maximum. Okay. And coming to the second point, the relation between input versus input between the two input variables. The relation between two input variables should be minimum, should be low, should be low. Okay. If the relation between input versus input variable, if the relation between input versus input, that is one independent variable to another independent variable, if the relation between one input variable to another input variable, if the relation between one independent variable to other independent variable, other independent variable is high, if it is high, then it is called as collinearity problem. It is called as collinearity problem, one of the most important. Collinearity problem. It is called as collinearity problem. Miss, what is the meaning of that? If the relation between independent to independent is very high or having a high correlation between them, then we are going to have a collinearity problem. What is meant by collinearity problem is one of the variable will not be significant. In the variable significance, we are going to see, right? In that, the p-value is not going to be less than 0.05. Okay, variable significance. In the last class, if you remember, I have shown you the variable significance. So here, let us take like this. In the last class, that is simple linear regression. Okay, in the simple linear regression, don't worry, I'm going to write once again. Here, if you see this, here the p-value, whatever the p-value is there, if independent variables are more, number of independent variables are there, and between the independent variables, any two independent variables are having the high correlation, then automatically you are going to have with the p-value will be greater than 0.05. For any one variable, the value will be greater than 0.05, and that problem is called as collinearity problem. So automatically we have to drop one of the variable. If there is a collinearity problem, then the solution for the collinearity problem means one of the variable we have to drop. Solution for that is variable should be dropped, right? So between the independent variables to dependent variable, the relation should be very high. Relation means simply to say correlation coefficient. Correlation coefficient. The relation means, what is the meaning of relation? Relation means, the meaning of relation means absolute correlation coefficient value. Absolute correlation coefficient value. Whether it is a negative or positive, anything is okay, but high value should be there. Either negative direction also high is okay, positive direction also high is okay. For example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If you make a relation between them, these two, you are going to get +1. The same relation, if you take like this, x and y, 1, 2, 3, 4, 5, 10, 9, 8, 7, 6. If you take, the answer is -1. They are inversely proportional to each other, but very strongly they are inversely proportional, right? So you can take in terms of either positive direction or negative direction. In the both the directions, if this is the case or this is the case also, we are going to predict easily the next numbers, and because the R square is going to be 100%, right? But if the relation between the independent variables, if the relation between the independent variables is high, then it is called as collinearity problem. Between the independent variables, if it is high, high means more than 0.5. If it is greater than 0.5, it comes under collinearity problem. Okay. So if you do, for example, encoding, one hot encoding or dummy encoding, Three categories are there. Three categories are there. And these three categories, you are doing the encoding. And if you keep all the three categories, automatically you can observe that collinearity problem will be there. There will be a collinearity problem. Okay, if the three categories are there, then you are going to get one problem called as collinearity problem. Okay, so in that case, what we have to do is we have to drop one of the variable. So that is the reason we are going to drop the one of the variable, dummy variable trap. Now, if you remember during the encoding, when I'm explaining the encoding concept, when I am explaining this encoding concept, in the encoding also I have told you the same. Just let me open this encoding. So whenever we are discussing the encoding, there I have told you this nominal encoding. Okay, for nominal encoding or one hot encoding, we have to drop the one of the variable. If you don't drop one of the variable, then it is called as dummy variable trap. Did I told that dummy variable trap? So you have to remove one of them. What is the meaning of dummy variable trap means? To n categories, we have to drop one of the variable by n minus 1. Otherwise, it is called as dummy variable trap. So dummy variable trap. When you derive one variable from other variables, there might be multi-collinearity problem. So if their values are two values are there, multiple values are there, you have to create only one value. Instead of one value, if you create two columns, then the relation between those two will be very high. If the relation between them is very high, automatically you are going to get a collinearity problem. Okay, means just if you want, you can check like this. Before checking, please you can write the notes this one. The relation between input and output should be maximum. At the same time, the relation between input versus output should be maximum. The relation between input versus input should be minimum. Just both are opposite to each other. Done. So if the relation between the two independent variables is high, then it is called as collinearity problem. Next one is called as multi-collinearity problem. There is one more option called as multi-collinearity. Now, what is meant by multi? Multi means multiple multi-collinearity problem. Next question they are going to ask you is what is multicollinearity problem? Now, what is meant by multicollinearity means, for example, let us take like this: x1, x2, x3, x4, x5 are there. 5 variables are there. Out of 5 variables, x1 and x2 are for having the high correlation. x1 and x2 are having high correlation. Since s1 and x2 are having high correlation, it is called as collinearity problem. Up to here, it is called as collinearity problem. Similarly, x3 and x4 also having the high correlation. x3 and x4 or x3 and x5. x3 and x5 are having the high correlation. Means one more set of variables. If one set of variables are having, then it is called as collinearity problem. Like that, we are having multiple sets. Multiple sets are having the high correlation. Then it is called as multicollinearity problem. You got the point? Individually, x1 and x2 is called as collinearity problem. And x3 and x5, these both of them are forming the collinearity problem. Since like this, how many sets of collinearity problems are there? 2 sets are there. Since more than one set of collinearity problems are there, they are called as multicollinearity. Like that, multiple are there, right? That is called as multicollinearity problem. Whether this one or this one, the answer is same. Just we have to drop the variable. Okay, whichever is forming the high correlation, that we have to drop the variable. How we can know that one means, just you can see that based on the correlation matrix. Okay, in the correlation matrix, as one of the student is saying that it is not audible. Guys, others, can you please confirm? My voice is clear? Clear on it, right? Done. Okay, done. So the correlation, the relation between y and x should be high. Between the y and x, y, what is meant by y means output, x means input. The relation between y and x should be high. The higher the value, the stronger the correlation, and you are going to get better the accuracy. This both should be very high. Whereas the relation between any 2 independent variables should be low. If the correlation between any 2 independent variables is strong or high, then it is called as collinearity problem, right? Now, just this collinearity problem, we are going to observe from the correlation matrix. So here, if you observe this one, this is the, either you observe the lower matrix or upper matrix, both are same. Either you have to observe upper or lower. Don't observe both of them. Either observe with respect to upper or lower. Now, second, in this first output variable, what is the output variable? This is the output variable. Whatever the output variable is there, remove this output variable. Forget this is not there. And you are having only x1 and x2 and x3. Now you have to observe between the TV versus radio, TV versus newspaper, radio versus newspaper. Now these three, out of these three, any one is having more than 0.5. The correlation value is more than 0.5. Then it is going to lead to the correlation collinearity problem. Now here, if you observe here, this is 0.78. That is good because this is the independent variable. This is the output variable. This should be high, good. And this one also should be high. That is also good. This one also should be very high, but here it is not having. If it is having a very good value, for example, instead of 0.22, if it is having 0.72 or something, it is best. As the higher the correlation we are having, the better the model. Okay, is that clear, guys? So between the independent and the dependent variable, that is input variable versus output variable, the correlation should be high. Between the input versus input, the correlation should be low. Is that clear? Yes. 0. Not 0.05. 0 if it is more than 0.5, that is 50%, more than 50%. Here 0.05 is there. It is less, just 5% only. The relation between them is 5%. Here also it is 5%. Here it is 35%. If it is more than 0.5, then it is a more than 50%. They are having the relation. Then it is called as collinearity problem, right? So here you can observe that collinearity problem. Now let us take one data set. Take a gender column. You create a gender column. take 10 values, male, male, female, female, male, male, female, male, female, 4, 8, 10. Okay. Now, if you do the encoding for this one, you do the encoding. If you do the encoding, one hot encoding, generally two variables are there. For two variables, whether they are nominal or ordinal first. They are ordinal or nominal? Nominal. Nominal means we have to do the nominal encoding. Nominal encoding means first we have to take female category separately, male category separately. So female, this one, first one belongs to male, 1, 1, 0, sorry, 1, 1, 1, 1, 1, 1, 1, 1. So remaining zeros. Right? Actually, we have to convert this particular column like this into two columns. Instead of converting to one column, we have to convert to two columns. After converting to two columns, what I have told you, you have to drop any one of the variable. That is either female or male. Drop first is equal to true means first one only will be dropped. That is female will be dropped automatically. If you don't drop, what happens? Can you calculate what is the correlation for this? If you calculate the correlation, if without dropping one of the variable, if you calculate the correlation, this correlation will be high. It is going to have a high correlation. Without dropping, just you try. Then, if they are having the correlation, obviously gender is a input column only, output column not, right? We are not going to predict the gender. What would be the gender? We are not going to predict that one. That is not going to be the output, input only. So gender is a input column. Now this one has a input, one of the input column. This is also one of the input column. Between the input to input, if between the two input variables, if the correlation is high, then what is the problem is called as collinearity problem. For that collinearity problem, what is the solution means? We have to drop one of them. Sir, I don't want to drop, sir. I will not drop. What happens? Let us see. Just apply the linear regression. Without dropping, just apply the linear regression. If you apply the linear regression, automatically assumptions will be failed. Automatically it will fail. 100% it will fail. So if the linear assumptions failed, now in order to for whatever the linear regression assumptions are there, in the assumptions it is going to fail. One of the fail. What it is going to fail means in terms of p-value is going to be greater than 0.05 and you have to remove that variable. Why we have to remove that variable? Because it is not forming the linear regression now. If p-value is greater than 0.05 means what is the meaning of that? Average line is better than the regression line. If average line is best means regression line is waste means how you can fit the regression line on that given data? It is failed one. How you can still fit on the failed one? So obviously we have to remove one of them. Right? That is the reason why we'll remove one of the variable. In the encoding technique, why we'll remove one of the variable? That is the reason. Is that clear now? Just if you want, you can check. And one data set, I'll share you one data set. Apart from this, I'll share you one more data set. For that data set, you do the encoding. After doing the encoding, take all the, instead of dropping one of the variable, you keep all the categories. Okay. For example, 3 categories are there, means create 3 columns and keep all the 3 columns and do the linear regression. Automatically, you can observe that problem, collinearity problem. Is that clear? Now, so if the correlation between any 2 independent variables are strong, then it is called as collinearity problem. For that, the solution is drop the variable. Either you, by seeing here itself, you can drop. Here itself, you can see and drop. Now the question is drop any one of them is the question. Which one has to drop? Out of 2, one you have to drop. Which one? That we are going to see in the variable significance. Which value is greater than p value is greater than 0.05? That one we are going to drop. Out of 2, one will be more than 0.05 now. That one. Which one is having more than p value greater than 0.05? That we are going to drop in the variable significance. Here, data cleaning is not required because there is no missing values. Already I have checked in the missing values earlier. There is no missing values in my data set. So no data cleaning is required. And no encoding is required. These 2 are compulsory. Missing values treatment and encoding is compulsory. Remaining outliers, scale, transformations, these are all not compulsory, not mandatory. You can apply that one in order to get the better accuracy. But they are not compulsory, right? Now here I'm going to take X variable. X is TV, radio, newspaper, and Y is says. And after that, I'm going to apply the train test split. And I'm going to take the train test split. And I'm going to apply the modeling. The modeling is first 3 lines of code. That is from sklearn.linear model, I'm going to import linear regression. And the model is equal to linear regression. And I'm going to fit on the X train, Y train. This time, what is the equation? What would be the equation? Earlier, the equation is beta 1x plus beta naught is the equation. Now, what would be the equation means? Beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta naught. Now, here I'm going to get 3 quotient values. The quotients will be 3. Beta 1, beta 2 and beta 3. Whereas intercept will be only 1. Beta naught will be 1. Now, sir, here 3 quotients are there. This quotient is related to what? That is 0.0456 into what? X1, TV. Why TV? Instead of TV, you can consider radio now. Why TV only? Because just you have to open the X-train data. In the X-train data, just click on the X-train. Open the X-train. Now in the X-train, whatever the order is there, that is the order of the quotient values. In the X-train, if you are having the first one newspaper, then automatically this beta naught is beta 1 is related to newspaper. Whatever the order you have given for the fitting the data. Whatever the order you have given here to fit for calculating. So you are asked to calculate for these 3, assuming this is X1 and this is X2 and this is X3. So for that, automatically this is beta 1, this is beta 2 and this is beta 3. So X1 is TV. Whatever the order you have given in the X-train data, that is the order, not the original data. Everyone will assume that raw data, not the raw data, which was given for the machine to learn, that data is important. Original data was given with maybe, for example, the original data X1, X2, X3, X4, X5. You may have the original data like this, out of which due to collinearity, you may drop X1. Now you have given only these 4 variables. Now the machine will give the output 4 quotients or 5 quotients. 4 quotients only, because you have given only 4. In the X-train, how many data, how many columns are there? That many quotients you are going to get. Is that clear? So in this, I'm having only with respect to X1, X2, X3, TV, radio, newspaper. Now for this, the beta naught is equal to 0.045 into TV plus 0.1882 into newspaper minus 0.001 into radio. Sorry, radio into news. This is radio and this is newspaper. Plus 2993.523. So this is y hat is equal to beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta naught. Is that clear? Now there might be a question. Sir, earlier simple linear regression. If I go with the simple linear regression, y hat is equal to beta 1 x plus beta naught is the equation. And you told that we are going to calculate the beta naught and beta 1 value based on the y minus y hat whole square should be minimum, for which we are going to apply this one should be minimum, where we are going to apply d by dx of sigma of y minus y hat, that is beta 1 x minus beta naught whole square. This should be minimum. So you are going to apply d by dx, and from this you have got the beta 1 is equal to sigma of x minus x bar into y minus y bar divided by sigma of x minus x bar whole square, and beta naught is equal to y bar minus beta 1 x bar. From this you have got like this. This is simple linear regression which you have explained the max. Now for multiple linear regression, how it is going to apply? Now in the multiple linear regression, y hat is equal to beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta naught in this example. Now same to same, ultimate goal is the errors should be minimum. The sum of the squares of errors should be minimum. This is the ultimate goal of any regression algorithm. The RMSE should be low. Okay. RMSE should be low means MSE should be low. MSE should be low means SSE should be low. That is sum of the squares of error should be low. Right. Now means nothing but you are going to apply d by dx of sigma of y minus the original y minus y hat. Now what is y hat? This is the y hat. That is beta 1 x1 minus beta 2 x2 minus beta 3 x3 minus beta naught whole square should be minimum. Instead of here 1, here you are having 3. Okay. Now from this we are going to calculate the first beta 1. How we are going to calculate the beta 1 means sigma of instead of x minus x bar, x1 minus x1 bar. First variable, that is TV. For the TV column, you are going to calculate the whatever the mean value into y minus y bar divided by sigma of x1 minus x1 bar whole square. Now beta 2, what is beta 2? Sigma of x2 minus x2 bar into y minus y bar divided by sigma of x2 minus x2 bar. Means separately you are calculating for each of them. You are applying simple linear regression for TV versus says, for radio versus says, for newspaper versus says. Separately you are doing. And beta 3 is equal to sigma of x3 minus x3 bar into y minus y bar divided by sigma of x3 minus x3 bar whole square. And finally, the beta naught is calculated as y bar minus beta 1 x1 bar minus beta 2 x2 bar minus beta 3 x3 bar. In this way, the beta 1, beta 2, beta 3 and beta naught is calculated. This is the max behind that. Is that clear? Done? So similarly, how we are calculated for a simple linear regression, multiple linear regression also same logic, no difference between them, right? But the ultimate goal, whether it is a simple linear regression or multiple linear regression or any other regression in the future, whatever the regression techniques we are going to discuss, the ultimate goal is the SSC should be minimum. The sum of the squares of error should be minimum. That is OLS technique. That is least squares method. Ordinary least squares method. Is that clear? Yes, you can write. If it is clear, you can write this one. This is the math behind that. How you got the beta 1, beta 2, beta 3 values means in this way. Beta naught values. Whether it is a linear regression or non-linear regression, whatever the equation, finally, y minus y hat whole square should be minimum. Inside that, if it is linear regression, this equation will be there. If it is non-linear regression, one more equation will come. Equation changes, but concept is y minus y hat whole square should be minimum. Okay. Done, guys? Okay. So in this way, it is going to calculate the beta naught, beta 1 and beta 2 and beta 3 values. So this is the beta naught value, beta 1 value, beta 2 and beta 3, right? Once it calculated these values, now as I have told you, modeling, once the modeling is completed, in the last class, just open the last class, what are the things we have discussed? First modeling, evaluation, followed by model selection. For every algorithm, 3 steps. First one is modeling. What is modeling? First, we have to import, save that one into a model and fit on the X train, Y train. Modeling is completed. So here I'm showing you intercept and the coefficients. In this case, I'm showing you the intercept value and coefficients, but generally in the real life, you don't need to print this one. This is not important for us. I'm showing to you the equation in the backend, how the equation was created and the model was created means this is the model, that is beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta naught. And in this equation, beta 1, beta 2, beta 3, beta naught values are saved here in the model. These 4 values are saved in this. And the equation was created. A new equation was created. Out of infinite number of values, this is the best equation which gives the minimum error within the linear relation. With using linear relation, within non-linear relation might be different. Within linear relation, this gives the minimum value. Okay. Now, once the modeling is completed, now next one is prediction. So I'm going to predict on the X test and I'm going to do the evaluation, that is R square value. If you want, you can calculate the R square value. If you want, you can calculate the RMSE value. And I have got the R square as 0.92, 92% is the test R square. Means test accuracy is equal to 92%. And if you want to calculate RMSE, means you are going to calculate the RMSE. How to calculate RMSE? From sklearn dot metrics, you have to import what you have to import? Mean squared error. You have to import mean squared error. And once you have imported the mean square error, and this mean square error, whatever you have imported, that is mean squared underscore error of the data. 2 values you have to give. Original value. What is the original value? Y test is the original Y versus predicted Y. What is the predicted Y? This is the predicted Y. That is test predictions. Okay. And you are going to calculate the mean square error. From this, you are going to calculate the mean square error. This is MSE. Okay. I'm storing this one as MSE. Which MSE? Test MSE. Test underscore MSE. This I'm going to store as a test underscore MSE. Now I want the test RMSE. I don't want MSE, I want RMSE. Test RMSE is equal to NP dot square root. You are going to take square root of MSE. You are going to take square root of MSE, which is nothing but test RMSE. Okay, test RMSE. So first you are calculating the MSE. From that MSE, you are calculating the RMSE value. For calculating RMSE value, you require the predicted values. So that is the reason here I'm doing the predictions. For calculating R square, you don't require the prediction values. Okay, prediction is not required for calculating the R square, because R square automatically it will only calculate and it will only substitute in the model. These values will be substituted in the model and it will only compare everything. Okay, first it will calculate the these X test values will be substituted in the model and it will calculate the Y test, that is predicted Y minus Y hat whole square sigma divided by sigma of Y minus Y hat whole square. So Y is there, X is there. So it is going to substitute in the equation and it will calculate the Y hat. In the X, it will calculate the Y bar, and 1 minus of this it is going to apply. Okay. So this is test R square. This is test RMSE. Now evaluation is done. Now next one is model selection. We have to check whether our model is a good model or a bad model. To check whether it is a good or bad model, what we have to do? We have to predict on the trained data and we have to compare with the original data. So I'm going to predict on the trained data. And here, if you want to calculate the RMSE miss, predict on the train. If you don't want to calculate RMSE miss, directly you can calculate the model dot square on X train comma Y train. So what is the train R square I have got? Train R square is equal to 0.88, which is nothing but 0.889, which is nothing but 88.9%. And coming to the test R square is equal to 0.925, which is equal to 92.5%. Both are between the plus or minus 5%. So it is a neither overfitted or underfitted. It is a good model and neither overfitted or underfitted. But for being a good model, this one condition is not sufficient. 3 conditions it has to satisfy. What are the 3? First one is it should not be neither overfitted or underfitted. Test accuracy should be equal to cross validation score, and it should satisfy the business problem. 3 things it has to do. And along with that, for linear regression assumption also it has to satisfy. Additionally, for linear regression assumptions. So now it is I'm going to cross verify with the cross validation score. Cross validation score CV is 0.887, which is nothing but 88.7. Test R square and CV again almost close to each other, between plus or minus 5% only, almost close. So this one is close, this one also close. So your test R square and train R square is equal. Test R square and CV also almost close to each other. So it is a satisfying the second condition also. Now what is the third condition? It should satisfy the business problem. In the business problem, in the given business problem, did they given any kind of particular minimum this percentage should be there? No, they have not given. So maximum, out of which whatever the maximum we can do, we have to try the best. So that is also satisfied. Now additional to that, what is the fourth condition? For linear regression, we have to check the assumptions. Now I'm going to check the assumptions. What are the various assumptions means? First, linearity of errors. That I'm going to see the errors are linear or not. So now here, if I observe the errors are linear or not, means I'm trying to fit a linear line. If I apply a linear line, can you see here? These data points are not having continuation. Only one area only it is having. Whereas this one continuation it is having, but this one only some part only it is having. Okay, that is again. Let us see the normality. Let us apply the normality. Now you can see here clearly the normality, whether it is a left skewed or right skewed. It is a left skewed, means normal distribution not satisfied. If one of them not satisfied also, overall assumptions were failed only. If fail means everything will fail. If satisfies means everything will satisfy. Sir, from linearity of errors, I'm not able to identify perfectly what is this linearity, and from scatter plot, we are not able to identify means. Just ignore this one and check for normality. If normality satisfies means automatically linearity also will satisfy. Right? Next, equal variance of errors. What I have told you, equal variance of errors means the positive errors and negative errors should be equal variance. Now in this case, let us see the positive errors we are having with up to maximum of 2000, whereas coming to the negative side, the errors are with respect to minus 3000. So almost okay. Now next, variables are significant. whether all the variables are significant or not. Let us see. Same code, whatever we have applied in the last class, same code I'm using. Nothing difference. Okay. Now this time you can observe this one. This is satisfied, but this is not satisfied. Okay. Sir, test accuracy 92%, sir, but still it is a waste model, sir. Test accuracy, though it is 92% also, if the variables are not significant, it is a waste model only. Now, then what we have to do? If assumption fades like this, or one of the variable is not significant, then what is the solution? Means the solution is we have to remove that particular variable. Whichever the value is greater than p value is greater than 0.05, we have to remove that one. The reason behind that is here in this case, the beta naught, okay, beta naught is not equal to 0 and not beta naught, beta 3. Beta 3 is equal to 0. Beta 3 is not equal to 0. What is the meaning of beta 3 is equal to 0, guys? Y hat is equal to beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta naught. If beta 3 is equal to 0, what is the meaning of this? This particular variable is not there. That is the meaning, right? So here beta naught is equal to beta 3 is equal to 0. Beta 3 is not equal to 0. This is null hypothesis. This is alternate hypothesis. Sir, why you have to consider in the null hypothesis beta 3 is equal to 0? Why? First tell me that reason. Why beta 3 should be considered as 0? We are assuming we are having total 3 variables. First variable is x1 is TV. x2 is radio. x3 is newspaper. 3 variables are having. Now, this XTV is saying that it is forming a linear regression. Linear regression. It is having a linear regression. Linear regression is there means beta naught value will be there. Beta 1 also will be there. If it is not forming a linear regression, average line is the best one. In this case, what would be there? Beta naught will be there. What about beta 1? Beta 1 is equal to 0. In this case, beta 1 is not equal to 0. Beta 1 is not equal to 0 means what is the meaning of that? Linear regression. Beta 1 is equal to 0 means what is the meaning of that? Average line. So null hypothesis says that average line is the best one. Alternate hypothesis says that linear regression is the best one. That is the meaning of that. Is that clear? And only for the first variable, forget about remaining 2, then remaining 2 are not there. Only for the first variable, beta 1 is equal to 0, beta 1 is not equal to 0. If the beta 1 is equal to 0 means average line. Don't apply the linear regression with TV. With that particular variable, it is not forming the linear regression. That is the meaning. Okay. This meaning is with x1 variable, no linear regression. That is the meaning of this. With x1 variable, there is no linear regression, no linear relationship it is having. With x1 variable, the output is having the linear relation. With x1, it has linear relationship. Is that clear? Now, since beta 1 is equal to 0, beta naught is equal to 0, then what I'm going to apply the test is one sample t-test. And I'm going to apply the one sample t-test. From one sample t-test, I'm going to get the output, the p-value. Based on the p-value, I'm going to decide whether we have to accept the null hypothesis or alternate hypothesis. So this I'm going to apply one sample t-test. See here, t-test. We are applying the one sample t-test. This is the t statistic value. Whenever you apply the one sample t-test, first you'll get the sample statistic value. For test statistic value, from the test statistic, you will get the p-value. Do you remember hypothesis testing? In that, whether we apply the z-test or whether we apply the t-test, whether we apply ANOVA test, for every test, first we will get the test statistic followed by the p-value. Similarly, here also, this is the test statistic value and this is the p-value. So this p-value, since the p-value is less than 0.05 alpha, p is less than alpha, p low, null go. What is meant by null go? This one. Now from this, what we are going to conclude? The x1 variable is having a linear relationship. Means you can consider this one. The first variable is having a linear relationship. Continue. Now from this, second one, variable number 2, that is radio. Radio, beta, whatever the beta value is there. For linear relationship is there, means beta 1 will be 0 or equal to 1. So here, once again, the same logic is applied for individually for the radio. Forget about the TV. TV already completed. With TV completed. Now the same logic you apply for the radio. Whatever the logic we have discussed above, now you apply for the radio. Now for the radio also the same thing. What is the radio? Null hypothesis is beta 1, whatever the beta value is there, this beta value is equal to 0. Slope value is not equal to 0. Slope, whatever the slope is there, the slope is equal to 0. Slope is not equal to 0. If the slope is equal to 0, no linear relationship. No, there is a linear relationship. If it is not equal to 0, means some slope will be there. Some slope is there. Some slope is there, means linear relationship is there. In this case, slope is equal to 0. If the slope is 0, means flat line, a normal line. Is that clear? So now again, I'm going to apply the same null and alternate hypothesis. Since the p value is less than alpha, p low, null go. Null go means we have to say that there is this one we have to cancel and we have to accept this one. What is this one? There is a linear relationship. So it is also having a linear relationship. It is also having a linear relationship. Now, third one. That is third variable. For third variable also, the slope is equal to 0. The slope is not equal to 0. Null and alternate hypothesis. If slope is equal to 0, no linear relationship. If slope is not equal to 0, there is a linear relationship. Since p value is greater than alpha, p value, what are the p value is there? This is 0.86 greater than 0.05. 0.05 is always fixed value. Level of significance of 5%. Right? Now, since why it is 0.05, you can see here also, this is 0.025 to 0.975. Means it is having a two-tail test. It is a two-tail test. This side 2.5%. This is 2.5%, in between 95%. Because it is a two-tail test. Now, equal and not equal means two-tail test only, right? So left side it is 2.5%, right side it is 2.5%, in between 95%. Right? Now, so it is applying the two-tail test, and based on the output, whatever the output I am having, since the output p value is greater than alpha, what we have to do? P high, null fly. What is null? Slope is equal to 0 and there is no relationship. If there is no linear relationship, why we'll have to consider that variable? If linear relationship is there, we are going to apply in the linear regression. If there is no linear relationship, why we have to take that one? So we have to remove this one. Is that clear now? The same thing you can see using the plots. This I have explained using the hypothesis test. The same thing you can apply by using the plots. The plots is called as AV plot. AV plot means added variable plot. What is meant by added variable plot means it is going to do the partial differentiation instead of doing the full differentiation. What is the difference between normal differentiation versus partial differentiation? If you are having three variables or more than two variables, that is x1 and x2. What is meant by partial differentiation? Partial differentiation means when you are doing this one, others are independent. Others are constant. We are not going to disturb the others one. Others are going to be constant. So in the earlier case, dy by dx, I have told you, and you have guys have written that one. Open that. Earlier SLR versus MLR d by dx, you have taken one equation, right? In that equation, instead of you are applying there full regression, instead of applying the complete normal differentiation, now you are going to apply the partial differentiation, that is dou by dou x. You are going to take dou by dou x of sigma of y minus y hat whole square. When you apply the dou by dou x, you are applying separately linear regression between TV versus SAES. A linear regression between radio versus SAES. a linear regression between newspaper versus sales. Separately you are going to do. That is the meaning of that one. Partial differentiation meaning is this one. Partial differentiation means you are applying the linear regression with each separately independent variables. When you are applying the linear regression between these two, the others two are constant. The others are constant. You are not going to work on the other variable. You are not going to touch the other variables. Now, if you observe the same thing, here I'm having the from statsmodel.api, whatever the statsmodel.api, I'm going to import the SM. In this SM, there is a plot part regression grid. This is the plot part means partial, a regression grid. So it is going to apply the partial regression. When it is applying the partial regression, and I'm going to get a AV plot like this. From this AV plot, you can clearly see that x of 0, that is x of 0 means TV. X of 0, here of x of 0, x of 1, x of 2 is there. Sir, what is x of 0 means? Just type clearly x. First you type here x. Now in this x, what is x of 0? If you write x of 0, what is the value you are going to x of 0? I'm writing x of 0. What you are going to have? X of 0? Nothing but first one. 0 is nothing but index error in this ilog. Just to apply the ilog. X dot ilog of 0. What you are going to get? First row, if you want with respect to column wise, all the rows and column is first column you are going to get TV. So 0 means 0 indicates the, what is 0? 0 indicates TV. 1 indicates radio. X of 0 indicates TV. X of 1 indicates radio. X of 2 indicates newspaper. Now from here we can observe this one. From the AV plot, you can see between x of 0 versus y, the relation between x of 0 versus y, that is TV versus sales. A linear line is there, which is participating in the linear regression, which we also concluded using hypothesis testing the same. Using the hypothesis testing, we also got the same answer. P is low, P is less than alpha. So there is a linear relationship between them. We also concluded the same using the hypothesis testing. Next, from this also we have concluded that between the radio versus sales, there is a linear relationship. From this, you can clearly observe there is an average line. Average line means from this also we concluded that the relation between these two is almost average line. So either by applying hypothesis test or by applying AV plot, both of them as per your choice. If you apply either AV plot also, the answer is same. From the AV plot also, you can conclude the same. Either by using that one also, you can conclude the same as per your choice, whichever you feel easy, that one. Right? Is that clear, guys? So now from this, we are going to remove this particular variable. That variable we are going to drop. Directly I'm going to drop. Now I'm going to consider only the TV and radio in my X variable. And I'm going to apply the train test split and everything. And now this time, whatever the values I have got, train R square is equal to 88, test of 92, cross validation of 88. Now in this case, if for now this whatever the data I'm having now, for this data, the variables also will be significant. The variables also will be significant. And from that, we are going to interpret the quotient values. Since I'm having the quotient of 0.0456, so for every unit increase in the TV spend, I'm going to have increase of 0.0456. Means for every $1,000, I'm having 45 units will be more. And in the coming to the quotient number 2, for unit increase in the radio, we are having the 0.187 units of the more sales will be there. For every $1,000, 187 units we can have. So if you are having more money, instead of spending on TV, spend on the radio. So in order to get the more amount of sales, we are going to conclude in this way. Okay. So If the variables are not significant, assumptions, if the assumptions fail, if assumption fail, then what we have to do? In that case, we have to remove the variable which is not significant. Remove variable which is not significant. This is one. If the assumption fail and whichever the p-value is greater than this one, that remove. Now, this is case number 1, which we have completed just now. Now, case number 2. Case number 2. Sir, x1, x2, x3, x4, x5. You are having 5 variables like this. Okay. Out of which p-value, this p-value of x1 variable is 0.01, which is less than 0.05. So I am considering this variable. P-value of this one is 0.5, 0.0, instead of 0.05, 0.5 means it is more than, so we should not consider. Next, p-value 0.08. This is also high. P-value 0.9. This is also high. P-value 0.04. This is okay. These two are okay. Now 3 variables are having more than p-value of 0. Like this. Should I drop all the 3 variables? This is the question. Whichever the p-value is greater than alpha, drop that variable I have told you. So now here 3 values are having more than alpha is equal to 0.05. When there is a collinearity problem, 100%, whichever the 2 variables are there, 2 variables, you are having 2 independent variables, right? 2 independent variables, 2 input variables are having high correlation, then it is called as collinearity. 2 independent variables are having the high correlation, then it is called as collinearity problem. In that collinearity problem, what happens means both the variables will have the high p-value. Both of them will have the high p-value. Then when we are having both of them high p-value, you have to drop any one of them. Now, which one we have to drop? If this is the case, which one we have to drop? Means if there is a collinearity problem, if there is a collinearity or multi-collinearity, if collinearity or multi-collinearity I'm having, either collinearity or multi-collinearity, then what I have to do? Means then we have to again remove the variable, remove one variable. In this case also remove one variable. Now which variable to be removed? The question is which variable? Which variable should be removed? Assume 2 variables are having the collinearity problem. X1, X2, X3, X4 you are having. Out of these two are having the collinearity. Since they are having the collinearity, the p-value is going to be greater than alpha only. That is 0.07. This is 0.09. Something you are having like this. Which are forming the collinearity, the 2 variables will not be significant. Both the will not be significant. Okay. Both of them will not be significant. If both of them are not significant, any one of them we have to remove. Which one we have to remove out of these 2? Means that we are going to decide based on the VIF value. We are going to decide based on the VIF value. What is meant by VIF value? VIF value is equal to 1 divided by 1 minus R square. That is VIF value. So just focus, instead of writing focus, clearly focus please. I'm having TV, radio, newspaper. 3 columns are there. Assume there is a situation where radio and newspaper are having the collinearity problem. These both has formed the collinearity problem. This I have observed in the correlation matrix itself. I have observed this one. There is a problem in the correlation matrix itself. I have seen this. There is a problem in the correlation. In the correlation matrix itself, I have observed they are forming the collinearity problem. Now, since they are forming the collinearity problem, though they are forming the collinearity problem, still I applied the linear regression. After applying the linear regression, TV is having the p-value less than alpha. The p-value is 0.03, which is less than alpha. Radio is having p-value of 0.06. Newspaper is having the p-value of 0.42. These both of them are having greater than alpha. Since these both are forming the collinearity problem, these both of them are having p-value greater than alpha. Now, out of these two, one of them I have to drop. Out of these two, one of them I have to drop. How to drop? Means we are going to calculate the VAF value of radio separately, VAF value of newspaper separately. Separately, we have to calculate these two VAF values. Whichever the VAF is high, that one we have to remove. How to calculate the VAF means, which is nothing but 1 divided by R square. 1 divided by 1 minus R square. Now, what is the meaning of first VAF? Let us understand. Forget about the formula. Okay, this is not important for us. First, understand the concept. What is meant by VAF? VAF meaning is how much this variable impacting the other variable. How much one variable impacts the other variable is called as VAF. Okay, VAF indicates that how much one independent variable impacts the other independent variable. Other independent variable. Other input, independent means input variable. Other independent variable. How much one independent variable impacts the other independent variable is called as VAF. Right? Now, here I'm going to calculate the R square. I told you R square. Now, what is the R square I'm going to calculate? Means here I'm going to apply the linear regression. Generally, linear regression has to be applied between what? Between what? Between input versus output. But here I'm going to apply the linear regression between input versus input only. Input versus input. That is linear regression between radio versus TV and newspaper. Means now I can understand how much this radio is impacting the TV and newspaper. I'll get R square for this, right? R square. What is meant by R square? R square means coefficient of determination. Coefficient of determination means how much it is determined, the value is determined based on the other values. Means based on these values, how much you are determining this one is called as R square. Similarly, I'm going to apply the linear regression on this, on what? Newspaper versus TV and radio. I'll apply the linear regression on them. Now I can understand how much newspaper is having the impact on the TV and radio. For example, radio is having very high impact, very high impact on the other variables, other input variables. It is having very high impact. And I got the R square value as, what are the R square? I have got the R square value as 90%. R square 90%. Now, since R square is 90%, now I'm going to calculate VAF, which is nothing but 1 divided by 1 minus 0.9, which is nothing but 1 divided by 0.1. 1 divided by 0.1 is nothing but 10. Right? Now, newspaper is having very less impact on the other variables. Assume this is the case. Newspaper is having less impact. Less impact means newspaper's R square is just 0.2. Now, what you are going to do? VAF is equal to 1 divided by 1 minus 0.2, which is nothing but 1 divided by 0.8, which is nothing but 1.25. Right? 1 divided by 0.8 is that one only, right? 8 by 10, 10 by 8, 5 by 4, 1.25, correct only, right? 1.25. So here the R square, the lower the R square means VAF will be low. The higher the R square means VAF will be high. So the higher the VAF value, that particular variable we are going to draw. Whichever the variable is having the highest VAF, that particular variable we have to draw. Is that clear? Whenever it is forming a collinearity problem, out of collinearity problem, the solution is we have to drop one of the variable between them. Which variable we have to drop means which is having the higher the VAF value. which has the higher VAF, that particular value we have to drop. How to calculate the VAF means 1 divided by 1 minus R square. R square here, whatever the R square is there, this R square is nothing but by considering whatever the variable, for which variable you want to consider, you want to calculate the VAF, that variable should be considered as the output variable. Okay, which one you are having? For example, I'm having x1, x2, x3, x4, x5. 5 variables are there. I want to calculate the VAF of x3. How to calculate? First, we have to apply the linear regression. On what? On what? Which one? Output variable is x3 is the output variable versus x1, x2, x3, sorry, x4 and x5. These you have to consider as the input variables, and x3 you have to consider as the output variable. By considering this one as the output variable, remaining 4 of them as the input variables, you have to apply the linear regression between them. After applying the linear regression, you are going to get the R square value for the x3 variable. And that R square, from that R square, you are going to calculate VAF of the x3 variable. That is 1 divided by 1 minus R square. Is that clear, guys? None? Whichever is having the higher the VAF, that particular variable we have to drop. Generally, if the VAF is greater than 4, that particular variable we have to drop. Any variable greater than VAF with 4, we have to drop. The reason behind that, what is the reason, miss? See, VAF is greater than 4 means, let us take VAF is equal to 4. 1 divided by 1 minus R square is equal to 4. The meaning of this one is 1 minus R square is equal to 1 by 4, which is equal to 0.25. 1 minus R square is 0.25 means, which is equal to R square is equal to 0.75. Wherever the R square is greater than 0.75, one variable is influencing with 75% on the other variable. More than 75% it is influencing. When it is influencing more than 75%, then that particular variable we are going to remove. It is influencing, right? So that particular variable we are going to remove. Is that clear? These are called as influencer variables. For example, in this class, for one of the student wants to do the mass bunk. He don't wants to come to the today's class. Assume. Generally in the college, in our degree college or engineering college, in our class, one student will be like that, right? Basically, he will be not interested. What he will do, Array, today we'll not have that one. So we'll say to the sir that today there is no class and we'll go outside, something. For one person, he'll get the idea, and others he will influence. Others also will be influenced based on him. That particular person is called as influencing person. We are going to remove this person. In the class, how to identify that influence person? Means individually for one variable to another variable. If he says others will listen, no. If he says others will listen, no. If he says others will listen, like that, I'm going to check with one student to other students. Now this student says means other says that yes sir, we'll listen. If they say like this, oh, this is an influencing character. Okay, we'll understand. Simple, right? Same to same. Right? So in this way, we are going to identify the influencing variable. That particular variable we are going to remove. This particular variable is influencing the other independent variables. It has to influence the output variable. It is influencing other independent variables. So it is a dangerous one. So we have to remove that one. Is that clear? That is with respect to linear regression. Now linear regression is completed. Now using the linear regression, now you check in the Google. Once after practice, you check in the Google and you type the interview questions on the linear regression. You will get all the interview questions. In that, most important interview question is, what is heteroscedasticity? Unequal variance of errors. What is homoscedasticity? Equal variance of errors. What is VAF? Variance inflation factor. Full form is variance inflation factor. Means how much one independent variable is impacting the other independent variable. Variance inflation factor, VAF. How much one independent variable is impacting other independent variables. Now, So if VAF is high, means it is impacting more. It is influencing more. If the VAF is low, it is not influencing. If the VAF is equal to 0, what is the meaning of VAF is equal to 0? No influence. No influence. It is not having the other independent variables. It is not going to touch also. It will not touch. There is no relation between, if you identify the correlation between X1 versus X2, the correlation matrix, if you take X1 and X2 like this, the correlation between X1 and X2 is 0. That is good, very good. The same correlation between X1 versus Y is 0. It is very bad. Between independent variables, the relation should be low. Between independent to output variable, the relation should be high. Okay. So now in this case, if the relation between X1 and X2, the correlation is 0, means very good. Very, very, very good. Because both are independent to each other. Now we can work. In this class, for your easy understanding, independent variables are students. Dependent variable is trainer, that is SRK. The relation between you and me, if it is high, it is a very good. You can ask whatever the silly doubts you are having also, freely you can ask. If we are having the rapport between you and me. If there is no rapport between you and me, I'm very strict or I'm very serious. If you are having fear to ask the questions also, then at the end, what happens means you'll not properly understand the things, and automatically at the end, you'll have with respect to no jobs. Automatically, it is going to impact. So if I'm having the good relation between the students versus trainer, then automatically you'll ask what are the doubts you are having, some from where you can study and how you have, and what is the problems you are having. Everything we can discuss, right? Now, between the independent variables, between the student to student, if the relation is high, what happens? If between the student to student, the correlation is high, it is going to lead to a collinearity problem. What is why? Between the student to student, if the relation is high, now they are depending on that particular student. For example, in this class, one student is depending on the other student. Whatever the doubts he is having generally, instead of asking the trainer, he is asking the other student and he is getting rectified. Now, in the company, are you going to depend on your colleague or you are going to depend on your senior? If you depend on colleague, automatically you can see the problem. There will be a problem. Because unless he is a very close friend of you, this person is close friend of you, okay. Otherwise, what happens means he is going to highlight. See, in the company, every person will not be a good person. Generally, for example, one person wants to show that he is a talented person. He wants to prove, for example, some X person, he wants to show that he is a talented. He is a talented. Two options are there in the company. To show that you are talented, two options are there. Option number 1, based on your subject. Based on your subject, you are going to prove that you are a talented person. Second option, option number 2. If you prove that others are waste, automatically you are talented only, right? If others are waste means you are better only. So in the company, many of the people will try second option. They'll always come and they'll say that, sir, this person is doing like this, this person. Hey, what you want to say finally? When compared to that person, I'm better. You want to prove this one, huh? Why are rising every time complaint on him? What you want ultimately, finally, what you want to say? Okay, he is a waste person. Finally, so since he is a waste person, you are a good person, obviously, right? In the companies, everyone will play the politics like this. Politics means not with Narendra Modi, Amit Shah. This is another type of politics. Next level of politics. That is direct. We can see it is visible. They'll fight to each other. They'll scold to each other. They'll abuse to each other. And for that, also TV channels will encourage. Fights are TRP. The more you fight, we get the more TRP. For us, no TRP, nothing will be there. Only fight will be there. That too Cold War. Silently it will be done. Back end only, not in the front end. Okay. So in the company, we'll have like this. In every company, we'll have. Always remember, we can't control this because others, if they are not having the subject, for them only one thing will they have called as jealous. Whoever the person not having the subject, obviously he will have the jealous. The person who is having the subject, he will not depend. Arey, what you feel? You feel like there is no time for me to discuss also related to this. You are not having the time. You are discussing. You are thinking about me. I'm not having the time also. I'll not even think about you. First, I'll think about my work. If my work is extraordinary, automatically I'll quit to another company and I'll get a better salary. You are not having the talent, so you can't move to the another company. You are having the fear that if you move to another company, you'll get a less salary. That is your fear. I'm not having that fear. If this job is not there, miss, I'll go to next job. I will get better salary. If I move, miss, I'll get the better salary. This person will have the confidence. This person will have the fear. These two things HR will observe in the backend. HR will encourage the politics. Generally, HRs will encourage the politics. Why? Because the more the negatives, we no need to give the bonus. By the year end bonus will be there, right? This negatives of this person will be highlighted by this person. Negatives of this person will be highlighted by this person. Finally, both will show their negatives. Finally, for both of them, there will be no bonus. HR will enjoy this one. If everything positives are there, HR has to pay the bonus now. Negatives are there. Exactly. Whenever you, almost 1 year, it is going to be completed. Means 1 year means 365 days. So next 15 days, in next 15 days, 1 year is going to be completed and you have to get the bonus. Now they'll start identifying the mistakes. Every day, one mistake. They'll say that every day, one, so that once the 1 year is completed, we can't ask the bonus also. What our inner feeling says that if I ask the hey, he is scolding. First, my job should be there. Later, bonus. First, my job should be there. Our feeling will be like that in that situation. These are all called as internal politics. You will face in the future. For that, all this solution is, if you are having this one, no one can do anything. If this job is not there, means next job. Nothing will be there. Just you can ignore all these things, right? So just remember this. Why I have told you this one is variation influence factor. One person will influence the other persons in the company also. In the companies also, VAF will be there. They are going to impact the others, right? So if they are impacting means just we have to remove them. So for that, what we have to do is we have to calculate the R square value. So first we are going to apply the TV upon the radio versus newspaper. And I'm going to calculate the VAF of the R square of TV. How to calculate R square of TV means, first just observe this. First, I'm going to take the SMF.OLS. Already I have shown you what is meant by SMF.OLS. So here you have seen that SMF.OLS, Y upon X. What is Y? Says earlier, what is X? X is nothing but TV, radio, newspaper, 3 of them. Now this time what I'm going to consider only the SMF.OLS of TV versus radio and newspaper. Only TV versus radio and newspaper I'm going to take. This is SMF.OLS. And now whatever that dot fit means it is going to fit the data. Now once the data was fitted, I'm going to store this one in a model. M is equal to, okay, I'm fitting. And M dot summary, I'm applying the M dot summary. Summary means what is the R square I have got? 0.05. How to get this value means just here directly after the fit, you can write dot R square. Dot R square. You can write here itself dot R squared. That same answer you can store in the M. Now you see the M value. What is the M value? Which is equal to 0.005. Is that clear? Dot R squared means directly it is going to store the R square value. Whatever the R square is there, it is going to store that R square only directly. Now this R square, now how to calculate VAF? R square is ready. How to calculate R square? VAF 1 divided by 1 minus R square. That is 1 divided by 1 minus this one. So first I'm going to calculate the R square of the TV, and from that I'm going to calculate VAF. Similarly, radio, R square of the radio, first I will calculate, and I'm going to do 1 divided by 1 minus R square of radio. I'm going to calculate newspaper R square separately, and I'm going to do 1 minus R square of newspaper, and I'm going to calculate VAF of newspaper. So like this, I'm going to calculate the VAF of TV, VAF of radio, and VAF of newspaper. Just nothing but see 1 divided by 1 minus R square. Just I'm typing here. Here my R square is nothing but M. Now what is the answer I'm going to get? 1.004. That is nothing but 1 divided by 1 minus 0.05, which is nothing but 1 divided by 0.95, which is equal to 1.005. Right? The same answer I'm going to get here. Is that clear? Similarly, I'm trying with the second one. Just try with the second one. That is radio. Just you check here. Now, what is the M value? First, what is the M value? M value is 0.12. That is, what is the M? Means R square value. Now, once the R square is calculated, what we have to do? 1 divided by 1 minus M. Now, what is the answer? 1.144. The same thing, 1.144. Is that clear? So similarly, I'm going to calculate the newspaper. For 3 values, I'm going to calculate. Now, in this, none of them is greater than 4. So there is no influencing. No collinearity problem is there in my data set. Since there is no collinearity problem, none of them is influencing other variables. But whenever you have having the collinearity problem, 100% one of the variable will be more than 4. Is that clear, guys? So if there is a collinearity, we have to remove that one of the variable. Right? Which variable we have to remove is which is having the higher the VAF. That is the linear regression. And in the linear regression, if the assumptions fails, how to overcome the assumptions means this is the one. In tomorrow's class, I'm going to show you overfitting problem. If there is a overfitting or underfitting, what is the solution and how we have to overcome that one? In the tomorrow's class, we are going to see. If there is a fail in the assumptions, how to overcome the assumptions that we have seen in the today's class. In the tomorrow's class, we are going to see if there is a overfitting problem, how to overcome. Is that clear? Any questions? If you have any questions, you can ask. Everything, please try to understand. Everything are connected to each other. Hypothesis test is connected here. Linear regression is connected here. And